Okay, year 12, welcome to our first video. So what I want you to do is to watch this video, and you can pause it or rewind it, do that at your own pace, and bring to the lesson a set of Cornell notes and any questions you might have. So it might be something that you want explaining more, or it might be a sort of challenging question that you want to ask, and bring those with you. Okay, so the topic for today is ionisation energies, and we need to be able to give a definition of ionisation energy. We need to be able to give equations. We need to be able to describe the factors that affect ionisation energy, and then we need to be able to compare ionisation energies of different electrons in an atom. So this definition here, first ionisation energy, is the official OCR definition. So that's something that you need to know off by heart, and it's a really easy way of picking up a few marks in the exam. So it's the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. We need to get each of these 4 bits right in order to get the full marks for the definition. So let's have a think about what that means. So they're gaseous atoms, separate atoms, not joined together as a solid or as a liquid. You've got 1 mole of them, and from every atom in that mole you're going to take an electron. So you end up with 1 mole of electrons, 1 from each atom. So if we call this an atom of element X, then from this we're going to produce an electron and a positive ion. So let's just have a think about where we got that positive charge from. In an atom, the number of protons is equal to the number of electrons. So overall, the atom is neutral. Now, the number of protons doesn't equal the number of electrons. You've actually got 1 more proton than you have electron, because you've taken one of the electrons away. So overall, you've made a positive ion. Okay, so let's do an example of this. So this would be X, which is a gas, becoming X plus, still a gas, and an electron. Now we actually have 1 mole of X, and we've made 1 mole of positive ions and 1 mole of electrons. But chemists are a little bit lazy, and so if it's a 1, we don't bother writing that in. So if we wanted a specific example, you could take a mole of sodium atoms separated from each other as a gas, and you would make a mole of sodium ions and a mole of electrons. Okay, right. Now we're going to think about whether that process would be endothermic or exothermic. So this would be quite a good stage at which to pause the video and go and get out your GCSE notes and just remind yourself about these 2 terms, endo and exothermic. Okay, so what I've done here is just drawn a hydrogen atom, really simple, 1 proton and 1 electron. So because these have opposite charges, they are going to attract each other. So if you want, and that's what holds the electron in that first shell around the nucleus. So if you want to remove the electron, you have got to overcome the attraction between that electron and the proton in the nucleus. So because you've got to overcome a force, you've got to put energy in. So first ionisation energy is an endothermic process. And the actual value is 1312. So the first ionisation energy of hydrogen is 1312. That's in kilojoules per mole. So every mole of hydrogen atoms requires that many kilojoules to take out an electron. Okay, so we're going to move on now to have a look at successive ionisation energies. With hydrogen, it only had one electron. That was all we could do, the first ionisation energy. But here I've drawn out lithium with its 3 protons and 3 electrons. And here we've actually got 3 electrons that we can pull away from the nucleus of that atom. So we can take lithium, a mole of lithium atoms, remove an electron from each one to make lithium plus. Okay, but this is successive, so from there, not back at the lithium atom, but from the lithium ion, we can remove an electron from 1 mole of lithium 1 plus ions, and we'll make lithium 2 plus. And from there, we could remove an electron from each ion in the mole of lithium 2 plus ions and make a mole of lithium 3 plus ions. So if we have a look at our equation, we had lithium as a gas, going to lithium plus, and that's the electron that we've removed, or a mole of lithium plus ions for the second ionisation energy becomes a mole of lithium 2 plus ions and a mole of electrons. Or you can take the mole of lithium 2 plus ions and take off another electron from each one to make a mole of lithium 3 plus ions. Okay, so to start off with, first ionisation energy is getting rid of that electron. So we've got now 3 plus and 2 minus, giving it a +1 charge overall. Then we remove one of the electrons from the inner shell. Now we've got 3 plus and 1 minus, so we've made lithium 2 plus overall. And we can pull off that third electron to make lithium 3 plus. So what I want you to do is to just pause the video now, and I want you to think about how these values are going to compare to each other. So the value for the first ionisation energy of lithium is 520 kilojoules per mole. I want you to tell me whether you think these ionisation energies, the second and third ionisation energy, would be more or less than that first ionisation energy, and have a think about being able to give an explanation about why it would be more or less. Okay, so here we have the 3 values, and we're going to have a look at those 3 values and use them to draw out the factors that affect ionisation energy. So if we compare the first and the second ionisation energy, you can see that there's quite a considerable difference between them. This number is about 14 times bigger than that number. So let's have a look at this slightly bigger picture of the atom, just so we can put some labels onto here. The first electron feels attraction from the 3 protons in the nucleus. But the second electron feels that same attraction but over a much smaller distance. So we've got a larger distance, which means that the force will be weaker. So this electron would be easier to remove. By that we mean that it would require less energy, so you can see that's why we have a smaller number here. But that's not all of the explanation. We also have between the outer electron and the nucleus, we have the electrons that come from the inner shell. And those electrons are negative, so between the inner electrons and the outer electron, there'll be some repulsion. But it's almost as if those electrons are already giving the outer electron a little bit of a push, and so it's much easier to pull that electron from the nucleus. So we've got some repulsion from electrons from the inner shell so that electron makes that electron that's feeling the repulsion easier to remove, meaning it takes less energy. So those are our two factors that explain the difference in those two numbers: the larger distance the force is acting over, and the repulsion that the outer electron feels from the electrons from the inner shells. Now this repulsion has a special name: shielding. So you remember, we draw a little shield there. It's forming a shield between the outer electron and the protons in the nucleus. Okay, so let's move on to have a look at the second and third ionisation energies. And you can see that this third electron definitely takes more energy. The difference between those two numbers isn't as big as it was between those two numbers, but this third electron is definitely harder. Now if we have a think about it, when we removed the first electron, there were 3 protons and 3 electrons. When we removed the second electron, there were 3 protons but only 2 electrons. And now we're removing the third electron, there's 3 protons and only 1 electron. So the ratio of electrons to protons has gone down. So as you're taking these electrons out, the 3 protons have less electrons left that they're pulling towards them. So they can pull those remaining electrons a little bit tighter in towards the nucleus, which means that there's a slight decrease in the distance between the protons and the remaining electron. And that slight decrease in distance means that force is slightly weaker, and so you need slightly less energy to remove it. So let's just have a look back and see what we were going to do. So we've done definition, we've looked at the equations, we've looked at the factors that affect ionisation energy, and then we've compared electrons from different levels, different shells, and we've compared removing electrons from the same shell. Okay, so do your corner notes, write down your questions, and I'll see you in the lesson.